In addition to the quantity of solute that's dissolved in a solution, we also need to know how the type of solute that's dissolved, because the type turns out to affect the properties of the solution that we are going to have. So for example, if you have salt water versus sugar water, first off, taste-wise is very different, and it also has different types of reactions that it could undergo. So what we want to do first is just present what kind of compounds can dissolve in water. We know water is a universal solvent. So it's a solvent for what? Well, there's three different types of solutes that we can dissolve in water. The first one is just ionic compounds. Remember that this is a huge category of things where you have a metal and a non-metal combining together. So you got to go back to your periodic table and look at where the metals are and where the nonmetals are. Some examples are sodium chloride, magnesium bromide, silver chloride, things that we've seen before. Another huge category of compounds that can dissolve in water are covalent compounds. These, remember, are just compounds composed of only non-metallic elements. So for example, ethanol, C2H5OH, sucrose or table sugar, which has the formula C12H22O11, acetone, something we use as paint thinner or other nail polish remover, CH3COCH3, and a lot of other compounds as well that will dissolve in water. And then the third category is something that's new that we've not talked about before, which is called acids. So typically we separate out compounds as ionic or covalent, but acids can do both. It's covalent, but when you mix it with water, it produces ions as well. So some examples of acids are HCl, HC2H3O2. So this one is called hydrochloric acid. Maybe it's something you've heard before. This one is called acetic acid, which maybe you have or have not heard, but it is the ingredient of vinegar. So let's take a look at how each one of these compounds dissolve in water. So an ionic compound, the way it works is you have the solid, let's say table salt, and they form this very tight structure. All the ions are stuck together. What water does when it dissolves the ionic compound is it sort of picks away at each of these ions. So you can see that it's kind of picking away all of these ions from the original solid. So it's just pulling them away one at a time. And the reason it could do that, remember, is because water is polar, and therefore the positive side of water can be attracted to the negative ion, and then the negative side of water, which is the oxygen side that's colored red here, is attracted to the positive ion. When you have covalent compounds, it's pretty much the same idea, except that covalent compounds don't break apart into ions. They're just in the solid phase or liquid phase. They're just stuck together like this, but they do have their polar parts. They have their positive side, they have their negative side. They're just not separated like ions. And so water does exactly the same thing. They're coming in and they're pulling away some of these solute molecules from the rest of them. And because there's so much water available, they're able to slowly take all of the structure away until nothing is left. Okay, everything looks like this at the end once they're dissolved. And then the last part is acids. Acids have both an H, which later on forms what we call a hydrogen ion or proton. So that has the symbol H+. And then it has an anion as well. However, without water present, the acid is just a covalent compound, but once water is present, water is able to come in and separate out the H+ from the anion. And so this is what it looks like. The H+, which is a positive charge, is going to interact with the negative parts of water, which is this red portion. That's the oxygen. And then vice versa, the anion in the acid will interact with the positive pole of water, which is the hydrogen end of water. So we categorize solutions based on the type of solutes that could form and their ability to conduct electricity. This was an experiment done maybe over 200 years ago on how we differentiate amongst different solutions. So we have three different types. We have strong electrolytes, weak electrolytes, and non-electrolytes. And they simply mean that if I were to take a light bulb that has a couple of wires coming off it and I put those wires into a solution, sometimes the light bulb will turn on really brightly, sometimes it will turn on just barely, sometimes it wouldn't turn on at all. And the reason why it does these three things here is because the quantity of electricity that's flowing through that circuit. If there's a lot of electricity, then there is going to be a really bright light bulb. This means there's only a little bit of electricity, and that means that there's no electricity. Now, electricity is just a flow of electrons. So when I take this light bulb with its two wires and I didn't put it in this solution, aqueous solution, the wires are not connected together, they don't form a circuit. When they don't form a circuit, then the light bulb will not turn on. When I put them in here, a circuit is formed, but the only reason the circuit is formed is because the electron is able to move from one side of the wire to the other side. In order for the electrons to do that, it has to go through ions. So unless you have ions in your solution, your light bulb is not going to turn on. So if you have a lot of ions, then you're going to have a really bright light bulb because there's going to be a strong flow of electrons. If you have very few ions, then there's going to be a weaker flow. We call that the weak electrolyte. And then lastly, if there are no ions, then there's no flow of electrons. We call that a non-electrolyte. So if you think about the two here, strong and weak electrolytes, there has to be at least some ions. With non-electrolyte, there are no ions whatsoever. So what are the type of compounds that could produce ions and type of compounds that cannot produce ions? Well, we're going to break them apart here. So the strong electrolytes contain the following categories of solutes. They can either be what we call soluble ionic compounds, and I'll talk about this in a second, but it's just ionic compounds, as you know, is just something with metals and nonmetals. Another name for ionic compounds is salt. So we use that term in chemistry, just referring to ionic compounds. And these are the ones that are soluble. That means they dissolve really easily in water. We also have categories of things we call strong acids. And then we have another category of solids we call strong bases. I'll talk more about these a little bit later in this chapter. Weak electrolytes are just weaker version of these three guys. So we have something called insoluble ionic compounds or insoluble salts. We have weak acids and weak bases. Again, they sort of behave the same way as that, except that they don't produce as many ions. And then we have non-electrolytes, which are solutes that dissolve in water, but they don't produce any ions at all. So the only thing that could belong in this category are soluble covalent compounds, right? So anytime you have covalent compounds, they're going to dissolve, but they're not going to produce ions, okay? Because the electrons are shared in covalent compounds. They're not being transferred from one atom to another. Now, I'm going to go back to this idea of solubility, which is how do we know that something is soluble or insoluble? We actually use a set of rules we call the solubility rules. I'm listing them right here. The idea is you can use this rule to help you determine whether something is soluble or insoluble. So now we're going to look at using the solubility rules to help us classify whether a solution with one of the following solutes listed on the left will be considered soluble or insoluble. So the solubility rules is shown right here. I'll work through this on the right side to think through how to use these rules. So the first solution we're looking at is AgBr. You need to see where either the Ag or the Br appears, and they're done from top to bottom. So when the first one says compounds containing group 1A metals, ammonium acetates, and nitrates are all soluble, then you have to check through to see if Ag or Br is one of those things. Well, group 1A metals in the periodic table, there's no silver there, and then none of the other ones listed there is either in an Ag or a Br, so we know that AgBr doesn't require that rule. So we're going to move to the second rule, which says most halides. So if you recall, halogens are in group 7A. So chlorides, bromides, and iodides, so what we call halides. So it says most halides are soluble. Exceptions include silver, lead, and mercury 1 halide. So what it's saying is that salts that contain either chloride, bromide, or iodide are going to be soluble, except if they're paired up with silver, lead, and mercury 1. And as it happens, of course, in our example here, we have a bromide, which is a halide, but it's also paired up with silver, so it's one of the exceptions. So this must be insoluble. So that's kind of how you go through it. Let's take a look at the second one. Calcium chloride. Rule number 1 doesn't really belong there with calcium chloride. Rule number 2, so remember chloride is a halide. So it says most halides are soluble except if it's paired up with silver, lead, or mercury. Well, in this case, it's chloride that's paired up with calcium, which means that it's just going to be soluble. Third one, lead 2 nitrate. If we look at rule number 1, it says everything containing group 1A, ammonium acetate, and nitrates are all soluble. So we hit that nitrates there. So this is going to be soluble. The next one, lead 2 sulfate. Rule number 1 doesn't have either of those ions in them. Rule number 2 doesn't have either of those ions either. It does say lead right here in the notes, but that lead has to be combined with halides, and we're not dealing with halides right now. We're dealing with sulfates. Rule number 3 says sulfates. Most sulfates are soluble. Exception include barium, strontium, silver, lead, and calcium. So it's an exception, so therefore this is insoluble. Lastly, copper 2 sulfide. Rule number 1 doesn't apply. Rule number 2 doesn't apply. Rule number 3 doesn't apply because this is sulfide, not sulfate. Rule number 4, hydroxides, doesn't apply here. Rule number 5, most phosphates, carbonates, chromates, and sulfides are insoluble. So we have sulfides here, so it should be insoluble except if it includes one of these guys, group 1A metals or ammonium. Well, copper is not a group 1A metal. It's also not ammonium, so therefore this is insoluble. So hopefully that helps you in using the solubility rules to predict the solubility of compounds.